Today, we're going to break down one of the most elegant and honestly surprising ideas in modern AI. It's called Bootstrap Your Own Latent, or BYOL for short. This is a method that really changes the game for how we teach computers to see. So let's get right into what makes this thing so revolutionary.
It sounds like a riddle, doesn't it? How do you teach a computer to recognize a cat without ever saying, "Hey, this is a cat"? But this is the exact question at the heart of a super powerful field in AI called self-supervised learning. And the answer? Well, it completely flips the script on how AI models can learn about the world around them.
You see, for years and years, the standard way we trained AI was through something called supervised learning. And it was a ton of work. You'd have to show it millions, literally millions of pictures, and each one had to be painstakingly labeled by a human. This is a cat, this is a dog, this is a car. And yeah, it's effective, but it's also incredibly slow and super expensive. This right here is the bottleneck that BYOL was designed to just completely break.
So what's the alternative? It's this idea of self-supervised learning, and the core concept is just brilliant. Instead of us feeding the AI answers, we give it a puzzle to solve using the data itself. And by figuring out the puzzle, it starts to learn these rich, meaningful features about the world, all on its own. No human ladles needed.
Now, before BYOL came onto the scene, the state-of-the-art in this whole area was dominated by an approach called contrastive learning. And to really get why BYOL is such a big deal, you first got to understand how these earlier methods worked. Contrastive learning basically works by playing a matching game. You take a picture, right? And you create two slightly different versions of it. Maybe you crop one or change the colors on the other. That's what we call a positive pair. Then you just grab a bunch of other random images to serve as negative pairs.
The AI's job is pretty simple, at least in theory. It has to learn how to represent each image as a string of numbers. The whole point of the training is to force the model to make the numbers for the positive pairs as similar as possible, while at the same time pushing the numbers for all those negative pairs as far apart as it can. It's basically learning to see what's the same and what's different.
But, and this is a big but, this method had some serious issues. To find good negative examples, ones that are tricky enough for the model to actually learn from, you needed to process these massive batches of images all at once. We're talking computationally a total nightmare. And the whole system was just really fragile. Its performance depended hugely on the exact little tweaks you made to the images. And this is where the story gets really, really interesting. The folks behind BYOL looked at this whole complex system of positive and negative pairs, and they asked a very, very bold question. What if you could just throw away the entire idea of negative pairs? Just get rid of them. What if an AI could learn just by looking at two different versions of the same image and just trying to make its representations match? I mean, it sounds way too simple to actually work, right? This is the big mystery, and the authors of the original paper state it perfectly. On paper, an AI trained this way should just fail. It should find a lazy, completely useless solution. But for some reason, it doesn't. Okay, so we need to understand what this word collapse means. Think about it. If your only job is to make your outputs match, the easiest way to get a perfect score is to just output the same exact thing for every single image. A cat, a car, a landscape, they'd all get the same meaningless representation. That's the collapse problem. And figuring out how to avoid it, well, that is BYOL's secret sauce. So how on earth does it do it? The architecture of BYOL is just incredibly clever. It's not one network, it's actually two networks that are constantly interacting and learning from each other in this really cool dynamic. So let's just walk through this. You've got two networks. One is called the online network, and it learns really fast. The other is the target network, and it gets updated much more slowly. So the online network sees one version of an image, and its job is to predict what the target network is going to say about a different version of that same image. The online network gets updated based on how wrong it was, but, and this is the key, the target network is only updated as a slow-moving average of the online one.
The best way to think about this is like a student and a mentor. The online network is the eager student, learning and changing with every single example. The target network is the wise mentor. It's basically a slightly older, more stable version of the student. So the student is always trying to predict what the mentor is going to say, and the mentor, in turn, very slowly incorporates the student's new knowledge. It's this constant dance.
So how does this whole student-mentor dance stop this system from collapsing?
It comes down to two key things. First, there's an extra little piece on the student network, a predictor, that makes the setup asymmetrical. And second, the fact that the mentor network is a slow-moving average means the student can't just cheat and control the answers. It's always chasing a slightly more stable, slightly outdated version of itself. And that dynamic prevents the whole thing from falling into a useless, trivial solution.
So, the theory is beautiful, it's elegant, but does it actually work in the real world? Let's take a look at the results, because they are seriously impressive.
On the huge ImageNet dataset, which is like the Olympics for computer vision, BYOL gets an incredible 74.3% top 1 accuracy. And remember, this is after being trained with 0 labels. This set a new state-of-the-art, and it wasn't by a little bit.
And here you can see it plain as day. BYOL isn't just a small step forward, it's a massive leap over the leading methods at the time, like SimCLR and MoCo. It's really playing in a different league.
But then, when you give BYOL an even bigger, more powerful network to work with, his performance jumps to an astounding 79.6%. Now that number starts to get scarily close to models that were trained on all 1.2 million hand-labeled images from ImageNet. It's learning almost as much, but without any of the labels.
And remember how we talked about those contrastive methods needing massive batch sizes? Well, this is where BYOL really shines. Look at SimCLR's performance. It just plummets as the batch size gets smaller. But BYOL, because it doesn't need all those negative examples, is remarkably stable. Its performance barely even budges. That makes it way more efficient and way more accessible for people to use.
It's also way more robust. A method like SimCLR is super sensitive to the kinds of image tweaks you use. If you simplify the task to just cropping images randomly, SimCLR's performance completely tanks, losing over 27 percentage points. BYOL takes a hit, sure, but it's far more resilient. The drop in performance is less than half of that.
And maybe the most important point of all is that the features BYO learns, they're not just good for classifying images. They transfer incredibly well to other, much more complex tasks. Whether you're trying to find specific objects in a busy scene or label every single pixel, the knowledge learned by BYO outperforms not only the other self-supervised methods, but in many cases, even models that were trained with full supervision.
So what this all adds up to is a pretty major shift in the field. By just getting rid of the need for negative pairs, BYOL created a simpler, a more robust, and ultimately a more powerful way for AI to learn from the endless stream of unlabeled visual data in the world. It really is an elegant solution to a very complex problem.
And this leaves us with a really fascinating question for the future, right? For so long, human effort, labeling data, was the fuel that powered AI progress. But methods like BYOL show us a path where AI can start to learn from the vast, unlabeled ocean of data all on its own. What kinds of new possibilities is that going to unlock?